Bismillah ar-Rahman ar-Rahim. We talked last time about finding properties of saturated liquid and saturated vapor and saturated liquid vapor mixtures. Today, in this part, we'll talk about finding properties of superheated vapors and later compressed liquid. And in these cases, we also, in most cases, we'll start looking first at the saturated liquid vapor mixture table, tables A2 and table A3. And understanding these tables, A2 and A3, is important. And also understanding the sketch of the phase change in the TV diagram and in the PV diagram, and how the constant pressure lines in the TV diagram behaves and the constant temperature lines in the PV diagram behaves. And that here, these lines here, the inside the saturated liquid vapor dome or region, this represents here the saturated pressure, and this line here in the TV diagram, represents the saturated temperature. So it's important to know that. Okay, let's look first at the superheated vapor. This region, as you remember, of course, whether in the PV diagram or the TV diagram, this is represented, or this is shown in the right side of the saturated liquid vapor region. So in the right side and also above the critical point, we have the superheated vapor region. Now, when do we know that our mixture is superheated? Before I start that, please remember that to define a state, so if we have system, this system is defined by properties, as we said, temperature, pressure, specific volume, internal energy, enthalpy, or any other properties. To define a state, we need two independent properties, and these independent properties will have to be intensive properties. So two independent and intensive properties. So all what we need are two independent and intensive properties, and there are different possibilities. We can have pressure and temperature. We can have pressure and specific volume, or temperature and specific volume, or internal energy and pressure or temperature, or enthalpy and pressure or temperature, or any combination of two properties. Now, how if we have these two properties, how we will know whether to look at the superheated tables or the compressed tables or the saturated liquid vapor tables. We already talked about the saturated liquid vapor region. Now, how to know that the property or the state is superheated? First, if the pressure is less than the saturation pressure at a given T. Remember, this is the PV diagram, and in the PV diagram we have lines of constant temperature. So, for example, if our temperature is T1, then this line, then our state should lie along this line only. So if we have T, so if T is T1, like this one, then we look at the pressure. If the pressure is less than the saturation pressure, this is the saturation pressure, as we said, right? This here is the saturation pressure, Psat. If the pressure that we have is less than the saturation pressure, then we know that we are in the superheated region, because it will be along this line. Okay? If the pressure is higher than the saturation pressure, then we are in the compressed region. That's the first case. Now, we can also look at the TV diagram. And in the TV diagram, we look at the temperature. So we look at the temperature. So if we have pressure, okay, then we look at the constant pressure line. Okay, this is in the TV diagram, and this is the constant pressure line. So assume that the pressure is 0.5. Then we look at the temperature. If the temperature is higher than the saturation temperature, and the saturation temperature is this is the saturation temperature, as we said. So if our temperature is higher than the saturation temperature, then we know that we are in the superheated region. If the temperature is lower than the saturation temperature, then we know that we are in the compressed region. And we know this from the table 2 or 3. So if we have the temperature, for example 85, and pressure, for example, is 0.5, okay, then we come here, we see that the at temperature of 85 degrees Celsius, the saturation pressure is 0.5783 bar. If our pressure is 0.5 bar, then our pressure is less than the saturation pressure. Okay, so here is less than the saturation pressure, so this is 0.578 bar, and our pressure is here. So which means that we are at that point of temperature of 85 and pressure of 0.5. Therefore, we are in the superheated region. If we would like to look at the pressure, then we can look here. So for example, if our pressure is 0.2 bar and our temperature is 70 degrees Celsius, so the saturation temperature of 0.2 bar is 60, but our temperature is 70. Okay, so here the saturation temperature is 60, but our temperature is 70, so it's here. Therefore, we are in the superheated region. So these are the first two cases. The other three are very straightforward. Okay, if the specific volume is larger than Vg, see here, this is the saturation vapor line. Therefore, this is Vg. This is the saturation liquid line. Then this is Vf. So if our specific volume is larger than Vg, then it means that the region is in the superheated region. Okay, so we look at the table A2 or A3 with P or 3. So here, for example, if we are again at 85 and our specific volume is 3, if our specific volume equal 3, okay, cubic meter per this, at 85 Vg, specific volume for saturated vapor, is 2.8, but our specific volume is 3, which means that V is larger than Vg. Therefore, we conclude that it's superheated. The same with the if the internal energy is higher than the internal energy of the saturated vapor. For example, if the internal energy at 85 is 3000, here the internal energy of saturated vapor is 2488.4. So if the interior energy is 3000, then we should know that superheated. If the enthalpy is 3000, then it's greater than 2651, which is the enthalpy for saturated vapor at 85. So this is how we use the saturated vapor, liquid vapor table to find whether we are in the superheated region or not. Okay, I hope that this is clear now. And this shows here superheated table, or part of the superheated table. The superheated table is in table A4, and in A4 we have table for each pressure. So this table here, okay, is for pressure of 8 megapascal or 80 bar, and this table here is at pressure of 10 megapascal, and so on. So if you go to table A4, you will see different small tables. Each small table is for different pressures, and the first column shows the temperature, and always the first temperature is the saturation temperature of that pressure and of this pressure. So these properties are the properties of the saturation pressure, saturation temperature of 8 megapascal, and you are given that the saturation temperature is 295.06. And these properties are for a T sat of 10 megapascal, which is 311.06 degrees Celsius. Okay, but then the rest here are so at temperature of 400. These are the properties at 8 megapascal, and these are the properties at 10 megapascal. So here, for example, find the we have superheated vapor at 10 megapascal and 400 degrees Celsius. Okay, then we at 10 megapascal, this is 10 megapascal, we have the saturation temperature 311, but our temperature is higher than that. So 400 is greater than T sat of 10 megapascal. Therefore, this is superheated. Then we go to the superheated. We look at the 10 megapascal table. We look at 400 degrees Celsius, and here we will have the specific volume. We have the interior energy. We'll have the enthalpy, and we'll have the entropy. Okay. Okay. What if? Okay, the temperature is not 400. What if we would like to find properties at 410 degrees Celsius? Here in the table we don't have 410. Then what should we do? Okay, we can apply the linear interpolation, and we use that when the exact value is not shown in the table. Okay, here for example we have this example that we have the pressure is 10 bar and the temperature is 215. So at 10 bar the saturation temperature is 179.9, but our temperature is 215. So 215 is larger than T sat at that pressure. Therefore, this is superheated. Okay, then we can go to the table, but here we find that the temperature of 215 is not in the table, so we need to use the interpolation, and the interpolation will be between 200 and 240 because it's between that. So it is good to write this, okay? So 215 is between 200 and 240, and these are the two values of the specific volume corresponding to 200 and 240. Then we use the linear interpolation, and I always like to draw this because it makes everything clear. So at 200, okay, the specific volume is 0.206. Okay, at 240, the specific volume is 0.2275. We would like to know the specific volume at 215. So here we see that this is increasing. Then this will be our point. Now we apply the linear interpolation. So this is triangles, two triangles, the big one and the small one, and these are similar triangles, so the ratios of the corresponding lengths are equal. Therefore 0.227 minus 0.20, so this length here, okay, divided by this length, okay, so the ratio of the big triangle equal the corresponding ratio, this one, which is V minus 0.206, okay, divided by this ratio, which is 215 minus 200. So these are equal, okay, and then so we multiply these two and find what is the value of V. So it's simple linear interpolation, and I advise you to practice this. So we are done with that. Now in the next part we'll talk about the using compressed liquid.